Alright, I got overwhelming support to make this video, so strap in, we've got a lot to talk about. This video will go over the entirety of the Super Mario Bros. 2 level format, and how the game transforms that level data into the tile maps and sprites that get displayed on screen. You'll get to hear about everything I had to learn about in order to create these level maps that I've used in these videos. It'll also cover how Subspace works and how levels are stored in memory in general, which will also answer a few of the questions I got in the comments of the previous video. Unfortunately, this will only cover the NES version of Super Mario Bros. 2, not the Famicom Disk System version, nor will it cover Doki Doki Panic or Super Mario All-Stars. This video is already long enough as it is, but I would like to look at the differences between the versions at some point. Let's get started. Retro Game Mechanics Explained is brought to you by its YouTube channel members, Patreon supporters, and viewers like you. Thank you. First, let's look at where the level data lives in the game's ROM. The NES's memory space allows for 32 kilobytes of program ROM data to be available for the CPU. However, Super Mario Bros. 2 uses 128 kilobytes in total, so it utilizes a mapper, the MMC3, to be able to switch what 32 kilobyte subset of the ROM can be available at once. The program ROM is split into 16 8 kilobyte banks, of which only 4 can be visible at once. All of the level data is stored in banks 8 and 9. When a room of a level is loaded, the game will tell the mapper to swap to these two banks so it can fetch level data from the ROM. Another thing included in these banks is a giant list of pointers that point to the locations of each level's rooms data. Just like in Super Mario Bros. 1, the data is split into two parts, background tile data and sprite data. The background tile data holds all the information about the blocks and tiles that make up the level layout, while the sprite data holds all the information about the moving objects and enemies. These are handled in two very different ways, so it makes sense to separate them into different lists. For the background tile data, there is simply one huge list of every room in the game in order. Now, in the final game, every level has 10 room pointers associated with it. If a level doesn't use all 10 rooms, the leftover pointers generally point to the same rooms as the first few. In this list, the first 10 pointers are for level 1-1, the next 10 are for level 1-2, and so on. We can use this pattern to determine where a specific room shows up in this list without having to search for it. Take the level number index, so 0 for 1-1, 1 for 1-2, etc., multiply that by 10, and then add the room index number. However, before this giant list of pointers is a short list that indicates the index of the first room of each of the game's 21 levels. Yes, there's a slot for 7-3, but it's a completely empty level. This would be necessary should there have been a variable amount of rooms per level. But I suppose it still helps because it allows the code to skip a calculation step. For the sprite data, though, I'm going to start a weird SMB2 code things counter because we're going to need it for this video. So the NES only has an 8-bit processor, but since it has a 16-bit address space, dealing with pointers is sort of annoying because they're always 2 bytes long. For the background tile pointer list, there are actually 2 giant lists. One list contains the top 8 bits of each pointer, and one list contains the bottom 8 bits of each pointer. If you need the 5th pointer in the list, you grab the 5th byte from each list and concatenate them. This is not a weird thing to do, in fact it's pretty standard. If you know you want the 5th pointer in a list, it's faster to read the 5th byte from 2 lists than to convert that 5 into a 10 and then grab the 9th and 10th bytes from a list where the 2 bytes of a 16-bit pointer live next to one another. However, the sprite data pointer lists are handled differently for some odd reason, so this will be weird SMB2 code thing number 1. Instead of using a small index table, it uses another pointer table. For example, if you need the level data for level 1-2, to get the background tile data, you'd look at the second entry in this index table, and it would tell you that the first pointer to 1-2's data is at index number 10. Simple. But to get the sprite data, you'd look at the second entry in a pointer table, and that would point to the first pointer to 1-2's data. This may seem not so weird at first, but remember that pointers are 2 bytes long. So really, you need 2 pointers, one to the high byte of the pointer and one to the low byte. This means that instead of a single list of indices, there are 2 lists of pointers for each level. And those pointers themselves are 2 bytes long, so there are really 4 lists of pointers to sprite data. For 1-2, you'd grab the second entry in these 4 tables, and those would form 2 pointers, one to each of the 2 bytes that make up the pointer that points to the first pointer to sprite data for each of 1-2's rooms. Yeah. Anyway, the game uses the level and room number of the currently active level transition to index into these tables and finds the location of the new room's background tile and sprite data. Regardless of how long the background tile and sprite data is for this room, 255 bytes are copied from ROM and stored in RAM, which means that most of the time it copies a bit more than it needs to. But it also means each portion of the level data needs to take up no more than 255 bytes, or else it won't all be copied over. Yes, weird SMB2 code thing number 2, it copies over 255 bytes instead of 256. This code could have easily been structured to copy 256 bytes. The index registers are 8 bits wide after all. But they specifically only copy 255 bytes. In fact, the 255th byte of the background tile data is copied twice, making it appear as the 256th byte as well. None of the levels ever use that much level data at once though, so it doesn't make a difference. Oh right, so the game is copying everything to RAM. If you've seen the Super Mario Bros. 1 level format videos, you'll remember that that game builds levels on the fly. This is mainly a restriction set by just how little memory the NES has. It can only store about 2 screens worth of a level in memory at a time before it has to start overwriting stuff that already disappeared off the left side of the screen, which is likely why you can only move in one direction in that game. In addition to the extra ROM the MMC3 mapper provides, it also provides a bunch more RAM as well. Enough, in fact, that an entire level's worth of background tiles can be loaded all at the same time, with some room to spare even. This is what Super Mario Bros. 2 does. And on this step, it is just copying the raw level data into a portion of RAM so that the mapper can swap over the program ROM banks to a different section of ROM, specifically those that have the code responsible for converting the raw level data into the individual background tiles that make up the entire level. In addition to tile data, sprite data lives here too, and the game regularly uses it during gameplay without needing to expand it out or anything. We'll look more into that later. The MMC3 mapper provides an additional 8 kilobytes of RAM, 2,400 bytes of which is dedicated to holding the entirety of the background tile level data. 1 byte corresponds to one 16 by 16 pixel block. There are 16 blocks across and 15 blocks down per screen, and levels can have a maximum of 10 screens, which is where this 2,400 number comes from. There is also an additional 240 bytes that hold one more screen's worth of tile data used for Subspace. I'll talk more about Subspace in a bit, but here's how the memory is mapped out. Each screen takes up 240 bytes, and there are 11 screens in total. The location in memory of each screen's data is not that important since the game also has a list of pointers. Sorry, 2 lists of pointer halves, of course, for each of these 11 screens. This is necessary again since the NES's index registers are only 8 bits wide and can only reference 256 bytes at a time, just enough for one screen's worth of data. So it's not a requirement that all these screens are contiguous in memory. In practice, they are, though, located at hex 6000 through 695F for the 10 main screens, and hex 700 through 7EF for the subspace screen, which is not in the MMC3's expanded memory, but back in the NES's standard RAM. When we get to the level building algorithm, some of the caveats that arise will make more sense if you realize that each screen has to be indexed separately instead of treating the entire level's data as one giant table. This pointer list has all 11 screens in order, but only the first 10 are used by the normal level. But this gives insight into what happens if you were to somehow find your way onto screen number 10. A common question in the previous video was what would happen if a level transition had an out-of-bounds screen index. 4 bits are reserved for the screen index, but screens normally only have indices 0 through 9. Technically, this index can be set to 10 through 15. If you somehow trigger a transition to screen number 10, you'll end up in the level data meant for Subspace, though it's still just treated as a normal level. The game doesn't know how to properly render the level past the 10th screen, but you do end up to the right of screen number 9, and you can jump back in bounds to the normal level, though graphics will start to mess up since it never expected the camera to end up out of bounds. Going to screens 11 through 15 results in this screen pointer list being indexed out of bounds, so you just end up with some super glitchy tiles and you fall straight through into the ground most of the time. Speaking of Subspace, let's take a look at how that works. The room transition to Subspace was one of the things I left out of the previous video since it doesn't use the standard transition logic. When you enter a door created from a potion, the game will copy the current screen's title data into screen number 10. The camera is locked in place since this is the only screen of Subspace that currently exists at once. The benefit of this extra screen is that the entire original level is still in memory, so when you return from Subspace, you don't have to wait for the level to load again, and all of the modifications you made to the level, like pulling up vegetables, will persist. Note that most of the time, this screen width of 16 blocks will straddle 2 different level screens, so it takes that into account. And of course, it reverses the order of the tiles so that the entire place looks mirrored. Normally, you can't see the graphics of the tiles in Subspace since they're all colored completely black, but they aren't flipped, just rearranged. Of course, tiles that have a non-symmetrical silhouette need to be fixed, otherwise this looks completely wrong. The game has a big list of tiles that need to be converted to Subspace form. It's pretty simple. Each tile is checked when it's copied to screen number 10, and if it needs to be converted, its flipped partner is written instead. There are 11 pairs of tiles that get swapped, and here's the full list. Except this isn't quite right, and here's weird SMB2 code thing number 3. This tile is incorrect in the data. Instead of swapping the left and right edges of this wavy platform, the left and center parts are swapped. Of course, you never really notice, since in Subspace both tiles end up completely black, but if you turn on the lights, it reveals just how big of a mess there can be. And actually, you can see this error only in 4-3. The snowy version of this wavy platform does not have a completely flat edge, so if you enter Subspace here, the only place where this platform is used, you can notice all of the small holes everywhere. Turning on the lights again reveals why it looks the way it does. There are a few other non-symmetrical tiles that are not on this list, though none of them really make a difference for not being here. The biggest offender is this rocky edge tile not having a mirrored version, which is visible if you visit Subspace next to the giant door in 6-3. Since we talked about Subspace, may as well knock out the weird jar transitions too. I left those out of the last video since they don't always use the standard room transition process either. There are actually 3 different types of jars, ones that lead to a normal sublevel, ones that lead to a general sublevel, and ones that are used as warp zones. You can't enter the warp zone jars from the normal world, so those are easy. But that leaves 2 types of jars. The jar that leads to a normal sublevel acts just like any other level transition, so I guess I could have included it in the previous video. But there's the other type of jar that leads to a generic jar sublevel. These jars disregard the level exit table completely and always go to this level's room number 4. This is dedicated to be the generic jar room. Since these jars don't abide by the normal level exit table rules, they can be placed right next to other level transition objects just fine, just like in the cave in 6-1. Whenever you enter a generic jar, it's treated a bit differently. A generic jar's background tile layout is limited to just a single screen, and that is because it also uses screen number 10, just like Subspace. This has a couple effects. First off, the generic jars load a lot faster, since they only have to load a single screen instead of 10. And second, since the room that has the jar is still in memory when you're in the jar, when you exit the jar, the level loads almost immediately since there's nothing to load. And third, because of this, again, any modifications made to the level persist. This is also why, if you use a glitch to bring a potion into a generic jar, the game will soft lock since it wasn't programmed to handle this case. Normally, potions explode when thrown in vertical levels. All of the jar rooms are vertical rooms, even if they're only one screen tall, since the game also doesn't handle entering subspace from a vertical room. The developers solved this by adding this failsafe to just prevent potion doors from appearing in vertical levels ever, even though they also never put a potion in a vertical room to begin with. The generic jar room is treated as horizontal when utilizing screen number 10, even though it is technically a vertical level. Weird SMB2 code thing number 4, I suppose. Okay, time to finally look into that level building routine. The level format is kind of similar to that of Super Mario Bros. 1, the concept is at least. Background tiles are stored separate from sprites, and those tiles are broken up into larger components, like green platform, vine, log, etc., while the main bulk of the level, like the ground and walls, are mostly built using floor patterns. The exact formatting of these objects is a lot different though, since the game was not restricted in ordering these objects from left to right, like in Super Mario Bros. 1. In fact, to explain everything more clearly, I'm going to focus on vertical levels instead of horizontal levels. Judging by the structure of the level building algorithm, it seems like vertical levels were more of the default style of level, at least at first. So it'll make more sense to introduce everything in the context of a vertical level, and then see what changes in the case of a horizontal level. Like I mentioned, there is one main benefit to having the entire level loaded in memory at once when it comes time to build it. This is that the objects don't have to be packed in order from start to finish in the compressed data. There's nothing preventing the game from adding background tiles to the level layout near the end of the level, and then going back and adding tiles to the start. The order doesn't matter at all. Now, in practice, it helps for stuff to be somewhat in order, since the level building routine goes in multiple passes. Objects are built going from the start to the end of the level, but at any time, a new pass can be initiated and new objects can be added on top of what already exists in memory. This gives more freedom when it comes to overlapping objects, and is also necessary to place certain objects correctly, since a lot of them don't have an explicitly defined length. But the very first pass is completely dedicated to the floor patterns. This gets the main structure of the level out of the way first. Then, one or more additional passes can be made to sprinkle the various platforms and such throughout the stage. A floor pattern is just a single row of 16 blocks. This pattern of 16 blocks is repeated row after row in the level tile data until another floor pattern object appears in the ROM data, at which point it switches. I'll talk more about the floor patterns when we get to that specific object in the level format definition. After the first pass, ordinary objects get placed into the level. Each object has an X and Y coordinate pair that defines where in the level it gets placed. The X coordinate ranges from 0 to 15 and denotes the X position of the top left corner of this object. The y-coordinate ranges from 0 to 14 and is treated more like an offset instead of a position. It denotes the vertical offset of this object's top left corner relative to the previous object's top left corner, or the top of the screen for the very first object in the list. So if two objects align vertically, the latter object in the level data will have a y offset of 0. This is why it's more efficient for objects to be stored in the proper order, since negative numbers aren't allowed here. There are ways which we'll see later to allow for objects to be stored in any order, but this offset method provides a quick and easy way to place a lot of objects in the level without wasting too many bytes for no reason. Now let's switch our level to be horizontal and see what changes. When it comes to floor patterns, instead of rows of 16 blocks, now the floor patterns consist of columns of 15 blocks. Instead of passing through the level from top to bottom, we go from left to right. In fact, the 32 floor patterns defined for horizontal levels are completely different to the 32 floor patterns defined for vertical levels. This is really useful since most of the floor patterns for vertical levels would be practically useless in horizontal levels had they just been rotated 90 degrees. Most of the vertical floor patterns consist of tunnels and walls on both sides, while the horizontal floor patterns are more about, well, floors. Now what about the order in which objects are placed? Weird SMB2 code thing number 5, it doesn't change at all. This might make it seem a bit more confusing, but objects still have an x position and a y offset. The y offset still measures vertical offset between objects, and the x position is just an object's x position relative to the left edge of the particular screen it is on. When the first object on a new screen is placed, its y offset is just the offset from the top of its screen plus the offset of the previous object to the bottom of its screen. In other words, pretend these screens were still stacked on top of one another like in a vertical level, and then the y offset between these two objects is still the y offset. This is the main reason why I believe vertical levels were the original level orientation when implemented, and horizontal levels came after. One final thing before we look into the level format definition. This has to do with objects that are bigger than one single background tile, so most of them. How do these objects handle crossing screen boundaries? For example, if we had one object that consisted of a chunk of blocks that was 2 tiles wide and 3 tiles tall, but it was placed at the bottom right corner of a screen, what would happen? Each screen of level data is 16 blocks wide and 15 blocks tall, so we can number each of the tiles from 0 to 239. Using the x and y coordinates of the object, the game can calculate the index of the tile of the top left corner of the object. Note that this y is the real y position within the screen, not the offset we saw earlier. And using the index of what we'll call the working screen, it knows exactly which byte in memory is the byte to write to. To demonstrate how an object writes multiple tiles to memory, suppose the working screen is screen number 0, and this object was determined to be placed at coordinates 5, 10. The tile index of the top left corner is pretty important, so let's call that the object's anchor point. In this case, we find the anchor point to be 16 times 10 plus 5, or tile index number 165. Screen number 0 is located at hex 6000 in memory, and then tile number 165 in hex would be A5, so the final memory address would be hex 60A5. This is the memory address that holds the byte corresponding to this single background tile. That's for the top left corner tile. To get the tile 1 to the right, we just add 1 to the object's anchor point, 166. To get the tile 1 down, we just add 16 to the anchor point, 181. And the next would be 16 plus 1 more, 182. And so on for the rest of the tiles. However, this becomes a problem near the edges of the screen. Let's look at the horizontal case first. If this object had an x position of 15 instead, its anchor point would be 175. If we try to get one tile to the right by adding 1, just like before, we get an index of 176. However, that corresponds to this tile way over here on the left side of the screen. Therefore, if we want to build this object correctly, we have to perform a boundary check. If we add 1 to the tile index and we notice it wraps around like this, we just have to make sure to update the current working screen number. Well, actually we don't want to modify the working screen number since that's important for building the rest of the objects in the level, but we can make a copy of it and make note that we are now working on the screen 1 more than the working screen. This is an important distinction which we'll see the importance of in a bit. Anyway, now that we're looking at the next screen, we can write the tile here. Except we're still 1 tile too low, since wrapping around like that incremented the Y position by 1, so let's subtract 16 to counter that. It turns out that some objects properly wrap to the next screen like this, and some do not. We'll say that an object is horizontally smart if it performs the screen boundary check. An object that is not horizontally smart will just stay within the current screen, wrapping back around to X position 0 with an additional Y offset of 1. Now, what if this object had a width of not just 2 tiles, but 18 tiles? If it was horizontally dumb, it would just wrap around again and shift down by another tile. However, a horizontally smart object will stay stuck on the second screen. In other words, it would not advance to a third screen. Weird SMB2 code thing number 6. This is because of that distinction I made earlier. When it's determined that we must advance to the next screen, instead of incrementing the working screen, we make a copy of the working screen index and add 1 to that. So any subsequent screen boundary crossings will just repeat this process and end up on the same screen yet again, 1 after the working screen. This phenomenon actually comes to our rescue later since it essentially prevents objects from being infinitely long. They are constrained to 2 screens at most. Okay, that was the horizontal case. Now for the vertical case. Things are pretty similar here. Let's say this object had a Y position of 14. This would make the object's anchor point 229. Should we try to add 16 to get the tile below it, we would get tile index 245. Now, this is a problem because screens only have 240 tiles, and this goes out of bounds into the non-existent 16th row. In this case, let's say we're in a vertical level. Again, we can perform a boundary check on our tile index. If we ever notice the index is greater than or equal to 240, we again make a copy of the working screen index and add 1 to it. This moves us to the next screen, and then to get to the top of that screen, we subtract 240 from the index. We can say that an object is vertically smart if it performs this boundary check. Similarly to horizontally smart objects, if an object is vertically smart, it is still restricted to 2 screens, so a very tall object will end up only extending over 2 screens maximum. What about vertically dumb objects? Well, they end up writing to that out-of-bounds index. Let's hold off on that for now and look at the next tile. This object was 3 blocks tall, so to write to the third row, we add 16 to the index again. This gets us index 261. Except, remember that the NES's index registers are 8-bit, so they can't hold any values greater than 255. That means the index actually wraps around and becomes 5, which is the top of the screen. This is analogous to the horizontally wrapping that we saw before, except there is no additional horizontal shift here. It all stays in the same column. And notice that this screen only had 2 rows of tiles written to it. What happened to the middle row, the one stuck in limbo out of bounds? So, since each screen is only 240 bytes, this is sort of undefined behavior. However, in practice, like I mentioned before, all 10 screens of level data are contiguous in memory. So the phantom 16th row of tiles of any screen are shared with the top row of tiles of the next screen. This means that tile number 245 of screen 0 ends up being the same byte in memory as tile number 5 of screen number 1. In a horizontal level, this looks very odd since some tiles end up being modified they're pretty far away from the base object. In a vertical level, this just has the effect of looking like the object extends one block further down than you would expect. It doesn't break at the screen boundary, but rather one tile past it. All of this screen wrapping is important because it means only horizontally smart objects can be placed over horizontal screen boundaries, and vertically smart objects can be placed over vertical screen boundaries. Not all objects are smart, and for those that aren't, it really restricts where they can be placed in a level. Oh yeah, for our original example of this 2x3 object placed at the bottom right corner of the screen, let's see what would happen. If the object was completely dumb, we would get one tile in the bottom right corner, one in the top right corner, two in the top left corner, and one in the top corners of the following screen. If it were completely smart, it would wrap across and down to the next screen properly, but in theory, the last two tiles would still end up on the second screen since, remember, smart objects can only extend one extra screen forward. There are no objects in the game that are smart in both directions, by the way, so this case doesn't really matter. These two tiles cross a horizontal and a vertical screen boundary, so without this restriction, they would have ended up on a third screen. A horizontally smart object would write the top two blocks straddling the two screens at the bottom, and the bottom two blocks straddling the two screens at the top. The middle two blocks would end up straddling the second and a third screen. This is an exception where the third screen comes into play. This is because these two tiles were written into the limbo out of bounds area of the first two screens, which corresponds to the top row of the second and third screens. And then a vertically smart object would actually have two different outcomes depending on the order of operations. If the 6 tiles were written in 3 rows of 2, it would end up like this, with just one tile at the bottom right of the first screen and the rest at the top of the second screen. However, if they were written in 2 columns of 3, it would be a bit different. The first column would end up on the right side of each screen, but an odd thing happens with the second column. To move from the first column to the second, 1 is added to the anchor point. This results in index 240, or the first out of bounds tile. So the first tile would end up on the top left corner of the second screen. Then to go down one row, 16 is added to the index. This results in index 256, which is too big for 8 bits, so it overflows to index 0. This vertically smart object would then perform this green boundary check, but 0 is less than 240, so it doesn't see any reason to move to the next screen. So the final 2 tiles would end up at the top left corner of the first screen. Now, none of the objects in the game are as complicated as this one, but if you got this example down, then the rest should be a piece of cake. And in fact, the level designers were aware of all of these screen wrapping limitations, so in all 20 levels of the game, there are hardly any cases of weird screen wrapping at all. But that's only because they knew which objects could cause issues, and made sure not to place them in problematic areas, like these pyramid objects that aren't horizontally smart. Alright, finally, I think we can get to the actual level data format. Again, the background tile data and sprite data are stored separately, so let's look at the background tile data first. The first 4 bytes of the tile data consist of the level header. This holds a bunch of global information about the level. Then comes a list of every object in the level. Most objects are 2 bytes each, but a small amount of them are 1 or 3 bytes long. Then the list of objects is terminated with a hex FF byte. Here's the format of the 4-byte level header. The most significant bit of the first byte signifies the orientation of the level. 0 if it's a vertical level, and 1 if it's a horizontal level. Bits 3, 4, and 5 make up the 3-bit palette index for this level's background. This can range from 0 to 7, but there are only 7 palettes defined, so setting this to 7 results in the color table being indexed out of bounds. Palette number 6 is also defined to be the Subspace palette, so really there are 6 different palettes to choose from. Now, each of the 7 worlds has a different color palette table, so really only each world is limited to 6 different level palettes. This will become a theme, as you'll see, each world having different definitions for certain things. The least significant 2 bits determine the palette index for this level's sprites. This is a 2-bit value, so it can range from 0 to 3, but only 3 palettes are defined, so sprite palette number 3 results in glitched colors. These also vary per world, but are definitely not as varied as the background palettes. The lower 5 bits of the second header byte determine the initial floor pattern of the level. Like I mentioned before, this ranges from 0 to 31. However, pattern number 31 is undefined. These do not vary per world, but there are 2 lists of floor patterns, one for horizontal levels and one for vertical levels. Skipping to header byte number 4, bits 3, 4, and 5 determine the initial floor pattern blocks. The floor patterns are made up of 4 different kinds of blocks, but those blocks are not hard-coded. This 3-bit value can range from 0 to 7 and picks from a list of 8 different block combinations that can be used for the floor patterns. This means each of the 31 floor patterns has 8 block sets to choose from, for a total of up to 248 different possible combinations. Most of the floor patterns don't use all 3 block types, so this is an overestimate, but it's still very powerful and much less limiting than the floor patterns in Super Mario Bros. 1. And in fact, each world also has its own block set lists, so that's up to 248 floor patterns per world. And also, in fact, there are separate block set lists for horizontal and vertical levels, so really it's double that amount. The lower 2 bits of this header byte determines which music track will play in this room. The upper 4 bits of the 3rd byte hold the length of this room in screens. Being a 4-bit value, it can range anywhere from 0 to 15, indicating 1 to 16 screens, but since the maximum number of screens the game supports is 10, this should never be higher than 9. The last 4 bits of this byte have to do with what tiles certain level objects are made out of. Bits 2 and 3 literally only affect how ladders look, so I'll bring this back up when I get to the ladder and vine mess. Spoiler, it's a weird SMB2 code thing. Bits 0 and 1 determine which solid blocks will appear in the level, affecting objects 3 through 9. This 2-bit value can range from 0 to 3 and picks from a list of 4 combinations of blocks that this level can use for these objects. In practice, only objects 3, 4, and 8 have different options, but objects 5, 6, 7, and 9 have the ability to be changed as well. It's just that the table of tile numbers just has the same tile fill all 4 slots. And like before, each of the 7 worlds have their own lists, allowing for even more variety. Now for the object list. Most objects consist of 2 bytes. The first byte holds the position and offset of the anchor point of this object. The upper nibble has the 4-bit Y offset from the previous object, and the lower nibble has the 4-bit X position within the working screen. The X position can range from 0 to 15, since screens are 16 tiles wide, and the Y offset can range from 0 to 14, since screens are 15 tiles wide. The second byte, and potential 3rd byte, is a parameter byte that defines the type of object, but it's used differently for different objects. Y offset 15 is unique. When an object has this value, it is treated completely differently. These are the special objects. For these, the X position isn't really an X position, but just another identifier to tell the special objects apart. For example, if a special object has X position 15, this would make the entire object's first byte hex FF. This is the sentinel value that marks the end of the background tile level data. X positions 0 through 6 are used for 7 different special objects, while 7 through 14 are unused and will likely crash the game. X positions 0 and 1 are a pair and are used to change the floor pattern mid-level. These special objects have 1 parameter byte. The lower 5 bits of this parameter make up the floor pattern index, 0 through 31, and the upper 3 bits are the offset into this screen to change the floor pattern. This counts as weird SMB2 code thing number 7 since it's sort of awkward. Since the Y offset is used up by the special indicator, 15, and the X position is used up by the ID of these special objects, the offset within the working screen to change the floor pattern had to be encoded somewhere else. We need 4 bits to encode an offset that ranges from 0 to 15, but we only have 3 bits left here. So that's why there are 2 special objects dedicated to changing the floor pattern. Special Object 0 will change the floor pattern at screen offsets 0 through 7, while Special Object 1 will change the floor pattern at screen offsets 8 through 15. And by offset, I mean horizontal offset in the working screen for horizontal levels and vertical offset for vertical levels. Another way of looking at this is to look at the upper 3 bits of the X position of this special object. If they're 0, 0, 0, then the screen offset is these 4 bits spanning across 2 bytes. Next, the special object with X position 6 will change the type of blocks the floor pattern uses. Weird SMB2 code thing number 8, this object allows for the lower 4 bits to form the index into the table blocks in the range of 0 to 15, even though each table is only 8 entries long. So if the 4th bit here is set, this will cause that table to be indexed out of bounds and a bunch of glitch tiles to be used as part of the floor. Next, if the X position of this special object is 2, then the working screen is incremented and the relative Y offset is reset to the top of the screen for the next object. This object and the next couple are only 1 byte long. If the X position of this special object is 3, then the working screen is incremented by 2 instead. This effectively acts like a screen skip and is useful for if there's a large space between objects. Since the largest Y offset between objects can only be 14 tiles, this allows for an offset larger than that. Special object with X position 4 is the one that indicates a new object pass. All this really does is reset the working screen back to 0, the start of the level. This allows new objects to be placed on top of any objects already built in the level. Finally, there is the special object with X position 5, which is the level transition object, and it's 3 bytes long. Basically, the 2 parameter bytes directly get stored in the level exit table based on the current working screen. As a reminder, the first byte holds the level ID 0 through 19, while the second byte holds the room ID 0 through 9 in its upper nibble and the screen to enter 0 through 9 in its lower nibble. Now for all of the standard objects. And yes, I'm going to go into depth into each object, since a lot of them have a lot of weird exceptions that I had to deal with when making those level maps. Before looking at each object, let's take a quick look at all of the tiles that make up these objects. A tile's ID can be anywhere from 0 to 255, since each tile takes up 1 byte, but not all tile IDs ended up being used. Just like in Super Mario Bros. 1, the top 2 bits of the tile's ID determines which palette it uses. 0, 0 for the blue palette, 0, 1 for the red palette, 1, 0 for the yellow palette, and 1, 1 for the green palette. Of course, with different level palette settings, these don't have to be blue, red, yellow, and green, but that's just the basic color of most levels, and it's the color of tiles I'll use for this video. Now, not all of these tiles can be used in the same level. Only graphics that are currently loaded in the current tile set will look correct. The tile set is determined by the world number. Worlds 1 through 5 use the grassy tile set, Worlds 2 and 6 use the desert tile set, World 4 uses the snowy tile set, and World 7 uses its own tile set. Some objects are only available in certain tile sets as well, but we'll get to those in a bit. A lot of the tiles are available in all tile sets, like the really common things like grass patches, doors, and jars. But some tiles also just have a different look in the different tile sets, such as mushroom blocks, these blocks, the big green platform, and the horizontal log turning into bones in the desert tile set. Each of the standard objects consists of 2 bytes, the first being the X position Y offset pair, like previously mentioned. The second byte determines which type of object it is. This byte is split into 2 parts. The upper nibble holds the object type and ranges from 0 to 15. There are three main groups of standard objects: those with object type 0 or 1, those with object type 2, and those with object type 3 or greater. I'm going to go through these in reverse order. If the object has a type of 3 through 15, then the lower nibble is treated as the object's length, which ranges from 0 to 15. Most objects add 1 to this value, giving a range of lengths from 1 to 16. Object types 3 through 7 are a single row of blocks with the given length. These objects are horizontally smart. These 5 different blocks depend on the setting found in the level header. Again, really only objects 3 and 4 use a variable tile, while 5, 6, and 7 are clumps of grass with small veggies, bridge, and spike tiles respectively. A special case is made for the bridge object. If the byte in memory that this tile is being written to has this exact tile already in it, hex A2, and it's getting overwritten, then the bridge with shadow tile is written instead. This is found, for example, on level 4-3. Object types 8 and 9 are a single column of blocks with the given height. These objects are vertically smart. While object 9 is always this rocky wall, object 8 again depends on that setting in the level header. Object 9 also always starts with this unique angled rock tile as the top tile in the column. Object type 10 is a ladder or chain with the given height, which is also vertically smart. I'm going to talk about all the caveats with the climbable tiles once we run into all of them, so we'll set aside these for now. But before we do, here's weird SMB2 code thing number 9. Objects 8 through 10 have a very special case programmed into them. Only if we're currently in level 5-3, room number 5, instead of writing a rock tile or a ladder tile or whatever tile, we write tile hex 22 instead. This happens to be Claw Grip's room, and the tile in question is the tile that makes up the pile of rocks behind him. See, Claw Grip wasn't in Doki Doki Panic. Originally, a third Mauser was found at the end of World 5. Claw Grip was added in the conversion to Super Mario Bros. 2, so it kind of makes sense that this tile had to be sort of hacked in. But the developers chose a very brutal way to insert it into the game. For example, in World 5, spikes are only used in this vertical room in 5-2. This room has a block type of 0-0 in the level header. The Claw Grip room has a block type of 1-0, so they could have taken advantage of the fact that the spike object is made up of one of the tiles that can be changed via this value, and used that instead. Oh well. Moving on to object type 11, this one is either a whale platform or a drawbridge cable. The determining factor is whether we're in World 7. Only World 7 will produce drawbridge cables. You can see one at the start of level 7-2. Otherwise, this object will be a whale, which only shows up correctly in World 4's tile set. The drawbridge chain is not smart in either direction, and the length of the chain is determined directly from the lower nibble of the parameter byte instead of being one more. That means it's possible to have a chain of width 0, in which case the chain becomes 256 tiles long. Due to the way the screen wrapping works, this ends up filling the entire working screen and the first row of the next screen with the drawbridge chain tile. The whale object is only horizontally smart. If you try to make a whale with a width of 1, meaning a value of 0, the whale becomes 257 tiles wide instead. However, because of the behavior of horizontally smart objects, the widest a whale will ever get is 32 tiles. You can see how the building algorithm fails by how it places the right edge of this whale inside of itself, since it kept looping writing tiles over and over in this screen. This is a common issue for platforms with unique left and right edges that we'll see more of later on. Whales do not have an explicitly defined height. Instead, they will always extend downward until they reach the screen relative Y offset of 12, since that is where the water level usually is. Placing a whale at Y offset 11 or higher will cause it to wrap around the bottom of the screen until it hits Y offset 12 again. Object type number 12 is the iconic wavy platform. It is also horizontally smart. Similar to the whale, it will glitch to 257 if given a width value of 0. It also has no explicitly defined height, so it will always extend to the bottom of the working screen and then stop before wrapping at all. This wavy platform has multiple forms. It looks like this in worlds 1, 3, and 5. In the desert tile set in worlds 2 and 6, it will look like this, and in world 4, it looks a lot different. If we're on world 7, this mushroom-shaped platform is built instead. This object has a few interesting details which apply to all versions of it except the world 7 type. If the corners end up overwriting another wavy platform, they will get swapped out for the appropriate tile that makes the layout look correct, such as filling in the little empty space in the corner. However, it is very weak in that it will fail to overwrite basically all other tiles. It sort of falls into the background. This object can only overwrite these 6 tiles, waterfall tiles, and the empty sky tile. Notice that these 4 tiles are not included in this list, which can cause some overlapping issues since they can't be overwritten. For example, if 3 platforms were written in this order, it would cause a weird tile to show up in the middle instead of being overwritten. But of course, this never happens in the original game because most of these platforms are placed in order of increasing Y position, which means they tend to get written from back to front from the perspective of the camera. Object type number 13 is this log platform, or this bone platform, in worlds 2 and 6. And object type number 14 is this cloud platform. Both of these objects are horizontally smart, but also fall victim to the 257 tile zero width bug as the previous platforms. The log platform has a special case where in World 5 specifically, if the ends of the log overwrite any tile, they will switch to a different tile. The left end of the log just melts into a centerpiece of the log, while the right end will get this unique tile that has the background filled in on the corners. This is so that the logs in these rooms in 5-3 look like they're growing out of the big trees in the background. Object type number 15 is a waterfall in almost all tile sets, but it becomes a chunk of these craggy rocks that poke out of the water in World 4. This object doesn't have unique left and right edges, so no 257 width bug, and it is horizontally smart. The waterfall has no explicitly defined height, so like the wavy platform, it will extend to the bottom of the screen and then stop without wrapping. The icy rocks behave similar to the whale, where the blocks will extend down to the water surface instead of the bottom of the screen. However, unlike the whale, if you place this object below the waterline, instead of wrapping all the way around, it will just stop immediately after just one row of rock tiles. Now let's look at the objects with type number 2. When the object's type is 2, the lower nibble of the parameter byte is treated as a subtype. All of these objects are just single tiles, so here's a table of them. We have all of the grass clumps with various items, the cherry, the 2 mushrooms, which use distinct tile numbers so the game can tell them apart, the Phanto tile that does not follow you around when you pick up a key, and the eye of the whale platforms. The mushroom tiles just show up as empty tiles in the overworld, but when they're present in Subspace, they spawn the mushroom sprite at their position. Same with the grass clump with the coin. These aren't normally found in the overworld, but when the tile data is copied over to the Subspace screen, all grass clumps are converted to this tile. Here's an interesting thing. The object with subtype number 15 is not defined. It ends up being this wooden tile that is only found in level 5-3, just by chance from an out-of-bounds table lookup. Actually, let's bring back weird SMB2 code thing number 9. Forget all that stuff with the spike tile, here's a perfect spot to insert that claw grip rock. This would have just required inserting a single byte instead of all that code to check specifically for one sublevel. Okay, the last group of standard objects, those with types number 0 or 1. When the type is 0 or 1, or I guess rather, if the upper 3 bits of the type are 0, 0, 0, then the lower 5 bits of the parameter are treated as a subtype. This allows for 32 more objects, which will cover all of the remaining objects in the game. The objects with subtypes 0 through 5 are 6 more single-tile objects. These include the mushroom block, POW block, rocks that can be blown up with bombs, which are available at any time regardless of the block type settings that we saw with the columns of blocks, the tiny jar, and a vine and ladder tile that you can stand on. These tiles are usually placed on top of vines and ladders where they poke out of a platform so that you can run across the platform without falling in the hole where the vine comes out of, unless you specifically climb down it. I think it's about time to talk about vines and ladders. This is going to be weird SMB2 code thing number 10. So before, we saw that standard object number 10 is a ladder, and it has a defined height. This allows ladders to be placed floating in air. Vines, however, are different. Standard objects with type 0 and subtypes 12, 13, and 18 are all vine objects. These objects don't have explicitly defined heights, so instead, these all extend in a certain direction until they hit a non-empty tile. Vines with subtypes 12 and 13 start at the anchor point and go down. Subtype 12 has a frond at the top, while subtype 13 does not. Both of these objects are unique in that they are the only objects to have special cases depending on if the level is horizontal or vertical. In horizontal levels, these vines will always stop at the bottom of the working screen and will not wrap at all. In vertical levels, however, these screens are vertically smart and will cross the screen boundary onto the next screen. These vines have no endpoint other than running into a non-empty tile. However, due to the behavior of vertically smart objects, crossing a second screen boundary will cause it to wrap onto the second screen yet again, which then causes it to basically run into itself, and the vine stops there at that screen boundary. This might seem weird, but I think it's reasonable since vines tend to be longer in vertical levels, so I'll let this one pass. The vine with subtype 18 starts at the anchor point and grows upward, which is also a unique behavior. This vine will always stop at the top of the working screen. Nothing is particularly weird yet, but do you remember those 2 bits in the level header I mentioned forever ago that had to do with how ladders are displayed? Let's see how those affect these 6 objects. So those 2 bits have a total of 4 different combinations. If they're set to 0, 0, then this is how the ladders and vines look. All is pretty standard. If these bits are set to 0, 1, then all ladders become chains. However, this does not change the ladder tile that you can stand on. Instead, this tile turns into a version that has a filled-in background, like it has a shadow behind it. If these bits are set to 1, 0, then all ladders are still ladders, but now they all have shadows, whether or not you can stand on them. And if these bits are set to 1, 1, then everything is normal, just like the standard 0, 0 setting, except the tile you can stand on still has a shadow behind it. So the settings in the level header only affect the ladders and not the vines. But say a level was using the chains setting. With this setting, there is no tile that looks like a chain that you can stand on. Here's how they ended up fixing that issue. Specifically, only if the current world is World 7, then the vine tile that you can stand on turns into a chain you can stand on. Which means that all of the rooms in World 7 use a mix of ladder and vine objects that just happen to both be converted into chains in 2 different ways. If we were to set the ladder setting to 0, 0 and disable this World 7 check, you would see that all of these chains are ladders, but the points at which you can stand on those tiles are vines behind the scenes. Since the chain tile that you can stand on can only exist in World 7, it cannot exist in other worlds. So for example, this chain in level 1-3, you might expect to be able to walk over it like any other ladder in the game, but instead you just fall right through. Moving onward, objects with subtypes 6 through 8 are the three types of jars. Jar number 6 is the standard jar that uses the normal level transition rules. Jar number 7 is the generic jar that always uses room transition number 4. And jar number 8 is the warp zone jar that you can't even enter from the overworld. Jars are vertically smart and will extend downwards until they hit a non-empty tile. They have a small quirk though. The jar's opening tile gets written at the anchor point, and the tile with the jar's body gets written downward until it reaches a non-empty tile. Then, the last tile that was written gets overwritten with the jar's base tile. Now, while the jar is vertically smart when writing the body tiles, it is not smart when it backs up one row to write the base. Remember how the vine object would run into itself if it extended down past the end of the screen after the working screen? This can happen with the jar too. But if it does, then when the game tries to overwrite the previous jar body tile, it subtracts 16 from the tile index. This causes the index to overflow backwards into the limbo area of the screen from behind, which results in the base of the jar being written onto the top row of the third screen. Now for doors, which end up being just as weird, if not more weird, than the ladders. There are 9 different kinds of door objects. Object subtypes number 9 and 10 are locked and unlocked red doors, respectively. Subtype number 11 is a plain black rectangle used for doors and cave entrances. Subtypes number 19 and 20 are plain white rectangles used for cave exits, with light rays coming out to the right and left, respectively. And object subtypes number 28 and 29 are those 2 arched doorways which were only used at the start of level 7-2. And yes, those count as real doors, despite you never being able to use them. All 7 of these doors contribute to weird SMB2 code thing number 11. Remember the level transition special object, the one that was 3 bytes long? That object is required for vine, ladder, and ordinary jar transitions. However, that is not always true for doors. Because of how common doors are and how they will always require a transition object, the developers tried to streamline this process. Whenever a door object appears in the level data, a transition object will follow immediately after, but without the special hex F5 byte. This effectively makes doors a 4-byte object with 3 parameter bytes, the last 2 being the level, room, and screen of the transition. Nothing weird here. In fact, this is a clever way to save a byte per door in the level. However, the weird part is that this only works in worlds 1 through 5. If a level appears in world 6 or 7, then every level transition, even door transitions, require the leading hex F5 byte. In other words, in worlds 1 through 5, doors are 4-byte objects, and in worlds 6 and 7, they're 2-byte objects. So yes, this means that the background tile level data format actually changes depending on which world the level appears in. Why in the world is this the case? Well, it actually has to do with the way the very first pass is done when the game is only focusing on all the floor pattern objects. During this pass, the game will ignore any standard object and only processes floor pattern and floor pattern block special objects, as well as the other special objects like the screen skipping ones and level transitions. However, it still needs to figure out how far in the level each of these objects appears. Since every object only contains its Y offset relative to the previous one, it has to sort of keep a running total of the Y position in the level. This means that even for standard objects, it has to at least look at their Y offset to march through the level properly. The issue is that at this point in the level building process, the game never checks what each standard object is, only that it is a standard object. Other than the doors, the only objects that are not 2 bytes long are special objects 2 through 5. So it assumes every standard object is 2 bytes long, even doors that have the extra 2 parameters for the room transition. This means that 4-byte doors will be treated as 2 2-byte objects. Now, Remember that the y offset for each object is held in the upper nibble of the first byte of the object. When these two lone room transition bytes are treated like a standard object, as long as the level ID contained within them stays within 0 through 15, its upper nibble will always appear as 0. Which is completely fine, since in theory the transition object should be tied to the door and have no vertical offset at all. However, if the level ID hits 16, then the upper nibble becomes 1, which would increase the y offset to 1. This would result in an inherent offset of 1 being applied to the level whenever a 4-byte door appears. Should there have been another object following the door that had a y offset of, say, 1 from the door, now it will be placed 2 tiles away, since the extra transition object sort of added 1 to this offset. And this would cause every object afterwards to be placed 1 tile lower than it should have been. So to counter this potential bug, the developers just disabled the shorthand in worlds 6 and 7, since level 6-2 is the level with ID 16, and this level onward would cause this problem. This was a very interesting decision, to say the least. There were definitely more elegant solutions, like checking each object if it was a door, and if so, making sure to skip over the extra 2 parameter bytes. Actually, this shorthand byte saving technique wasn't really necessary in the first place, since the level with the largest background tile data was this room in level 6-3, and it only used 218 out of 255 total bytes. The only other level to reach over 200 bytes is this room in level 3-3 with 205 bytes. Okay, pushing all that aside, we still aren't done with doors. There's 2 others that don't even use this hybrid room transition thing. But first, there's one last thing to say about this door, the one where the light shines out to the right. All of the other doors we've seen so far are a fixed size, and none of them are smart in either direction, by the way. However, this one has a special case applied to it when it appears in World 6. In this case, the door is not only 2 tiles high, but will just extend down forever until it hits a non-empty tile at the base of the door. This is used specifically only in this room of level 6-3 as the right half of this big cave entrance. The left half is also its own object with subtype number 21, which is basically the same as the right half of the door, except it doesn't include the light rays coming in. And also, it always extends down to the ground, not just in World 6. However, this is the only level where it was used. And of course, the final door object, the one with subtype number 30, is the outside entrance to this exact door, again, only used once in 6-3. This object is also not smart and is simply a big chunk of 3x9 tiles that comes with door tiles built into it. Let's go back to the tall door object without light rays. We have to talk about weird SMB2 code thing number 12, which involves the objects with subtypes number 21, 22, and 15. We already saw object number 21, which is this door that extends down to a non-empty tile. Well, subtype number 22 is a similarly behaving object. It's this tree background element. It also extends downwards until it hits a non-empty tile. Both of these objects are vertically smart, so they will extend to the neighboring screen. However, they also have a weird special case in the event that they are found in a level in World 5. If these objects are placed in World 5, the tall door object is instead a tree as well. There's no difference between these 2 trees at this point. I honestly have no idea why this is the case whatsoever. But additionally in World 5, these objects go from being vertically smart to just stopping at the bottom of the screen entirely without wrapping at all. This attribute is also found in object subtype 15, which is a pillar object. This object appears as a different kind of pillar depending on the world. Again, vertically smart, except for in World 5 where they just stop at the screen boundary. The entire reason to make an object vertically smart is so that if they're used in a vertical level, they can be placed near the edge of 2 screens and span across them, alleviating some of the pain that comes with designing a level with all of these weird edge cases. However, in the final game, this tall door and tree object never appear in a vertical level at all. And the only times this pillar object shows up in a vertical level, in levels 7-1 and 7-2, they don't even cross screen boundaries. Of course, maybe they did in a previous iteration of these levels' designs. But as it is now, none of these objects needed to be vertically smart in the first place. The reason why their behavior was changed for World 5 was likely because of these two areas in levels 5-2 and 5-3. In 5-2, these tree objects extend down into these bottomless pits at the bottom of the screen. It may look like there are some rock tiles down there, but all of these objects were included in the same building pass. And since objects are built from the top down, that means that these tree objects get built before the rock platforms. So there's just empty space down there at first. Then the rock tiles overwrite the bottoms of these trees. In this instance, building the rock platforms first, and then going back and adding the trees on a second pass would have prevented this issue. And in 5-3, these pillars just extend down into this bottomless pit. If the pillars were vertically smart here, they'd poke into the top of the adjacent screen. A possible solution would be to add a ceiling to the level up here, so that the pillars would stop at the bottom of the previous screen if they were smart. Alternatively, these pillars could have sat on blocks, similarly to how the trees sat on the rocks in the previous level. Continuing onward, just a handful of easy objects left to go. Object subtypes 24 and 25 are big chunks of brick background elements. These are always 6 tiles wide, horizontally smart, and extend downwards until they hit a non-empty tile or the bottom of the screen. If either of these objects appear in World 7, they use a different tile and look like this instead. Object with subtype number 31 is the big tree trunk background element. It's always 12 tiles wide, horizontally smart, and also extends downward until it hits a non-empty tile. It is not vertically smart and will wrap around vertically instead of stopping at the bottom of the screen. Object subtypes number 16 and 17 are the 2 tile wide and 1 tile wide cloud background elements. The big cloud is not horizontally smart, so it can't be placed at the border of 2 screens. Object with subtype number 23 is the pyramid background object. This one also extends downward until it hits a non-empty tile, but it is not smart in either direction. This greatly affects where these can be placed, since a really big pyramid is pretty much locked into being placed in the center of the screen, or else one of its ends will wrap around the screen boundaries. Object with type number 26 is the veggie machine spout found in Wart's room. This is just a simple 2x2 block of tiles that is not smart in either direction. Just this object alone won't spawn any veggies though. There's a corresponding sprite that needs to be placed in the level in conjunction with these objects. Object with subtype number 27 is the drawbridge chain again, but this version of it is glitched, so it might just be some leftovers from old code. It's possible this used to be the original drawbridge object and it didn't share a type with the whale platform. The reason why this is glitched is because it calls the exact same routine in the game as the other drawbridge object. However, this version does not have an explicitly defined length at all, and that routine expects the length of the currently processed object to be in a certain memory address, and that variable never gets written to in this case. So the length of this drawbridge chain will end up being whatever that variable last held the last time it was used. Most of the time it ends up being 0, as objects will decrement this length variable as the object is being built, using it as a sort of counter. And if you remember from before, when the chain has a length of 0, it ends up drawing 256 tiles that fill up the entire screen. And with that, I have saved the best object for last, the object with subtype number 14, the starry sky background element. We're going to have to look at some assembly code for this one. In case you aren't familiar, this is the object that is responsible for placing the stars at the top of the screen in some of the nighttime themed levels. These stars were placed using a random number generator. Now, this would be pretty cool. However, the RNG is seeded using the same value every time, so while the layout of the stars is random, they'll be the same in every level. Let's look at the code real quick. It's not too complicated, really. The first thing it does is something every object does and makes a copy of the working screen index so that the original working screen index isn't overwritten. Then it seeds the RNG with the two values 128 and 49. Then there's a big loop here that will write all of the tiles. This is a nested loop since first it will loop through all of the columns in the level, and then for each column it writes a tile only in the first 3 rows in the sky. Inside the loop, it first generates a random number using this subroutine. Here's what the RNG function looks like. It's fairly similar to a couple RNG functions I've already covered in previous videos, so I'll spare the details for this already long video. Whatever random number this subroutine generates gets bitwise ANDed with 7, which results in a random number between 0 and 7. This is used as an index into a table that has 8 values corresponding to the 8 tiles it can choose. Here is that table, which consists of 6 empty sky tiles, 1 small star tile, which is literally only a single pixel, and 1 big star tile. This means that for each tile that can possibly become a star, there is a 1/8 chance it will be a small star, 1/8 chance for a big star, and a 3/4 chance it will stay empty. The Y-index register here holds the index of the current tile of interest on the working screen. After writing this tile ID to the big table of level data, the game moves on to the neighboring tile below by smartly moving down. Now, this object doesn't have a chance to be vertically smart because if the index ever becomes 48 or greater, it will bitwise AND this index with 15, which effectively snaps the index back up to the top row. This is how it limits the stars to only appear on the top 3 rows of the screen. After snapping back up to the top of the screen, it moves to the tile's neighbor to the right. Here we can see that this object is horizontally smart since it uses this subroutine to add 1 to the tile index and checks for screen boundaries. Remember, the weird thing about horizontally smart objects, though, is that they can only move a single screen farther than the object's anchor point. This is because the subroutine takes the value of the working screen variable, adds 1, and then stores it to the working screen copy variable each time. So these values never differ by more than 1. However, this object just throws that out the window because the next step is that it overwrites the original working screen variable with the copy. This means that this object can extend over more than just 2 screens, which is pretty necessary if its job is to cover the entire level with stars. Doing this would make the object infinitely long, but the next comparison here checks to see if the working screen index ever hits 10, which would indicate that it reached the end of the maximum length of a level. In which case, it will exit this loop and wrap everything up. Since this object ends up clobbering the working screen variable like it's not supposed to, it restores it here by setting it to 0. This has the effect of acting sort of like the new object pass special object. The only difference here is since it's a standard object, the first pass, where the game only handles floor patterns, it would completely skip over the object and not reset the working screen to 0. So, in order to keep things in sync, it's important that this object always appears on screen 0. And that would also ensure that the entire level gets covered with stars. Now, I'll let that one slide as far as weird things go, but I won't excuse a bug in this code that went undetected. So here's weird SMB2 code thing number 13, which causes the very first screen of a Starry level to never have any stars. You could stare at this code forever and probably never even notice what's wrong, since it's really the lack of something that's the issue. This Y-index register holds the tile index of the currently written tile. However, this routine never loads the object's anchor point into the Y register. Every other object at the start of their building routines starts off by readying up this Y register. But for some reason, this object does not. It was just left out on accident. Which means that the effective anchor point of the Starry background object is not whatever coordinate is specified by the object in the level data, but by whatever the Y register happened to be right before this routine runs. And that value happens to always be the constant 30. In the game's code, there are a handful of jump tables, which are just big lists of pointers to functions, one for each of the types of objects. There is a subroutine in the game that is responsible for executing a jump table jump, and within that routine, the Y register is used. Its final value is determined by the index of the pointer in that particular list. In fact, it ends up as the pointer's index times 2 plus 2. Remember how this starry background object has subtype number 14? That means the pointer to this build routine has index 14 in the jump table, and so the Y register ends up being 14 times 2 plus 2, or 30. Treated as a tile index into the working screen, 30 corresponds to the tile in the 15th column and second row on the screen. Since this object loops through tiles column by column, that means the first 14 columns and the first tile of the 15th column get completely skipped over and will never become a star. And since the RNG is seeded the same way every time, we know that the first 10 tiles to be written are never a star either. So the first tile to become a star is the 11th, which means that the entire first screen of a level will never have any stars, even if the object is placed at the top left corner of the first screen. This could have been fixed with a single LDY instruction here right before the main loop, a single instruction that pretty much every other object has. And that's it for objects. We're only halfway done because now it's time for sprites. Okay, just kidding. The sprite data format is considerably simpler, so there's way less to talk about here. Unlike the background tile data, which is compressed into smaller format and expanded into each individual tile that makes up the level, the sprite data format is itself the data that sits in RAM that the game uses to determine where sprites show up in the level. There's no decompressing or building step that needs to take place. So let's look at this format. First off though, we run into weird SMB2 code thing number 14. Remember how background tile screens are 16 tiles wide by 15 tiles tall? This is the case for horizontal and vertical levels. Well, when it comes to the context of sprites, they live in screens that are 16 tiles wide and 16 tiles tall. This doesn't make a huge difference for horizontal levels, but for vertical levels, this means that there are two coordinate systems going on at once. This unfortunately has to do with the architecture of the NES, since its name tables are 32 by 30 characters in size. Those are 8 by 8 pixel tiles. However, in order to make the math work for stuff like hitbox collisions, there just can't be a gap of 16 pixels every screen. So in vertical levels, there's a tile Y coordinate, which rolls over to a new screen every 15 blocks, and a sprite Y coordinate that rolls over to a new screen every 16 blocks. Which I presume would make it very confusing to design a vertical level manually, since tiles and sprites don't share the same coordinate space. Anyway, there is no sprite data header, since all the important global level details were stored in the background data header. The sprite data comes in blocks, 1 block per screen. The first byte in a block holds how many bytes of data there are in this block, including this byte itself. Unlike objects, every sprite is 2 bytes long with no exceptions. So in other words, this byte should be the number of sprites that appear on this screen times 2 plus 1. This means an empty screen would just consist of a block with a single byte, 1. There is no terminator hexFF byte like with the objects. The game relies on the fact that the sprite data should not end before the end of the level's tile data, otherwise this data could start to be read out of bounds. After the length byte is just a list of each sprite on that screen, and each sprite consists of 2 bytes. The lower 7 bits of the first byte is the sprite's ID. The upper nibble of the second byte is the sprite's X position on this screen, and the lower nibble is its Y position. There are no offset shenanigans, just positions relative to the top left corner of each sprite screen. And that's really it. Let's quickly go over each of the sprite IDs. Sprites that have multiple different versions have different IDs. So like the different colored Shy Guys and Sniffets have unique IDs. Some sprite IDs correspond to combo sprites. These cause more than one sprite to spawn. For example, the Albatos with ID 10 will spawn carrying a bob-omb. Sprite number 13 is a Ninja that runs around, and number 14 is a Ninja that jumps in place. Sprite number 18 will spawn a magic carpet and a Pidgeot riding it. Sprites number 21 and 22 are enemy generators. They act as spawn points for other sprites, which were commonly used with those tiny jar blocks. Sprite number 23 is the Phanto that will chase you when you carry a key. Number 24 is a Cobrat that jumps in and out of a jar, while number 25 jumps out of the sand and runs around. All of the bosses are in here too, as well as projectiles. There's only one Birdo sprite. It depends on Birdo's X position in the level that will make her pink, red, or gray. A Birdo with X position 10 on the screen will be pink, and X position 11 will be red. All other positions make her gray. Sprite number 45 is specifically the Hawkmouth boss. The 4 Sparks each have 2 different properties. Number 46 and 47 move clockwise, while the other 2 move counterclockwise. And number 46 and 48 move slowly, while the other 2 move quickly. Farther down this list, we come to all the various items and things you can pull out of the ground. Sprites 50 and 51 are the generic veggies that look different depending on what world you're in, and the veggie at number 52 represents the extra types of veggies that come out of the veggie machine to provide more variety in the final wart fight. Sprite number 57 is a mushroom block, which is specifically the version of the block that you carry in your hands. When a mushroom block is sitting in a level, it is a background tile. Same thing with the POW at number 58. And Sprite number 60 is specifically a door to Subspace. Sprites number 71 and 72 are sprite generators that will cause enemies to appear from the sides of the screen. They will continue to spawn over and over until Sprite number 73 is loaded, which is the generator killer. And Sprite number 74 is the sprite that spawns veggies that is used with the veggie machine spout objects. Sprites with IDs numbers 75 through 91 are unused and will likely crash the game. Now, sprites number 92 through number 127 are interesting. When these sprites spawn, they take on the sprite with ID that is 64 less than their own ID. For example, sprite number 92 becomes sprite number 28, which is Birdo. These sprites all act as world bosses. All this means is that however and whenever this sprite despawns, it will trigger the end of the world fanfare and spawn a door. So this wasn't really used for Birdo, but for the world bosses like Mauser and Triclide. Of course, in the original game, only boss sprites were given this treatment, but for example, sprite number 127 is a boss mushroom sprite, so the moment you pick it up, the game treats the world as completed. The last thing to tackle is that most significant bit in the first byte of each sprite. This is where the game takes advantage of the fact that this sprite data has been copied into RAM. This bit is the currently loaded flag. If the sprite is currently on screen somewhere, this bit will get set to 1. The moment the sprite dies or otherwise despawns, this bit will get reset to 0. This is how the game knows not to respawn something if it's already on screen. Otherwise, you could pick up a Shy Guy, move away and come back, and they would spawn again. This is the only spawning flag that sprites have, which is why if a sprite gets killed, it will just respawn again. This video wouldn't be complete without an example. Let's look at this small room in level 2-2. Suppose it was our job to take this designed level and convert it into compressed level data format. We'll start with the background tiles, so ignoring the sprites. We can split the level into 2 parts, the walls and floor, and all the other objects within the room. Let's focus on just the blocks and stuff. We need to identify what tiles belong to which objects, as well as each object's position relative to the top left corner of the screen they're contained within. There are 5 grass objects over here. 1 has a POW, 1 has a potion, 1 has a big veggie, and 2 have small veggies. These will all be their own objects. I'm going to write each object's parameter bytes in hex on their anchor point, leaving out the first byte that holds their x and y location data since we'll be calculating that later. This mushroom will also be an object, specifically the second one found in this level. The door is an object, and since we're in World 2, this will be a 4-byte door. This white door with light shining to the right has type and subtype hex 13, and it takes you to level 2-2, level ID 4, room 1, screen 5. Then there's the cherry and this grass tile that holds a 1-up, and also these 3 grass tiles that all hold bombs. Now there is a single object that consists of a row of grass tiles, but those will only give small veggies. For any other planted items, they have to be placed individually, so this will be 3 individual objects. That leaves us with these brown blocks and these rocks. The brown blocks can be made out of 4 rows of tiles, and the rocks can be made out of 2 columns of tiles. At this point, we'll have to pick which block types we want to use in this room, and we have 4 options. Unfortunately, the row of brown blocks and the column of rocks belong to 2 different sets, so we can't use these objects at the same time. Fortunately, there is an alternative object that is just a single rock regardless of the block type setting. So we can just use the setting that gives us the rows of brown blocks, but we'll have to insert these 6 rock tiles as 6 individual objects. Now we can focus on just the walls and stuff, which will be built out of floor patterns. We also need to pick the floor pattern blocks, which in this case will be the option that just gives all rocky tiles. Looks like there are 10 distinct floor pattern segments. So the first floor pattern will go in the level's header, and we'll need 9 floor pattern objects throughout the level data. Now that we've identified all of the objects that will be in the level, we can form the object list. Well, first comes the 4-byte level header. This is a horizontal level that uses background palette 1 and sprite palette 1, so the first byte becomes 10001001. I'm just going to write 0 to any of the unused bits here. The initial floor pattern is the one that's completely filled in, which is pattern number 10, so the second byte becomes 0001010. This level has 3 screens, doesn't have any ladders, so that setting doesn't matter, and we determined we need the block type setting to be 00, so this third byte becomes 00100000. And the initial floor pattern blocks are all rocky tiles, which is index 3, and the music will be the underground theme, which is music index 1, so this final byte becomes 00011001. In hex, this turns things to 890A2019. Now for the big object list. We have to think like the level building algorithm though, so we need to start at the top of the first screen, work our way down adding objects top to bottom, and then move on to the next screen. So let's focus on the first screen. We have 9 standard objects and 2 floor pattern special objects. Remember, the first one goes in the level header. Special objects don't have an inherent position associated with them, so they can appear anywhere within this screen's data. However, floor pattern objects do need to appear in order within themselves, just due to how the game keeps track of the current floor pattern. A floor pattern shouldn't be the first object in a screen's data, since it relies on the working screen number being in sync, which is only done when a standard object is placed on a new screen. So why don't we go ahead and put the floor pattern special objects at the end of each screen's data. Scanning down from the top, the first things we hit are these grass tiles and the mushroom. The order of the X positions of objects within a row doesn't matter, other than that objects later in the list will overwrite those earlier in the list, of course. Whichever object comes first will have a Y offset of 8, but the other 3 will have an offset of 0, since they're contained in the same row. Let's just do these left to right to make it simple. The first grass clump will have hex bytes 8B28. Then the next 3 objects will be 0D26, 0E2D, and 0F22. Then comes the first row of brown blocks with an offset of 1, then this grass tile and this row of blocks, then the third and fourth rows of blocks. Now for the floor patterns. Remember, here's the weird way that floor pattern objects are encoded. This first one is at offset 5, so the T bits here become 0101, while the floor pattern is 23. In binary is 10111. This results in the hex bytes F0B7. The second special object here is at offset 7 and pattern number 16, resulting in the bytes hex F0F0. That's all for this screen, so we move on to the next. We hit this rock tile next, and it gets a Y offset of 5, since it's on the third row of this screen, and it picks up an additional 2 rows left over from the previous screen. The other 5 rocks follow, along with this grass tile way over here. This screen has 4 floor pattern special objects, so toss those in. Then the final screen, which consists of the door, its extra 2 parameter bytes, the cherry, the bombs, the 1-up, and finally, the last 3 floor pattern objects. And to finish up this list, we finalize it with a single hex FF byte at the end. This is almost identical to what the original game uses for this level, however, we're missing one object. Turns out we haven't escaped the weirdness, and here comes weird SMB2 code thing number 15. So a room transition object is assigned to a particular screen, if you remember from the previous video. When a room transition object appears in the level data, this makes any transition object like door or vine within the screen use that transition. But it's not the position of the object that is referenced, it's the position of your character. Normally this distinction isn't necessary since you need to be on top of a door or a vine to use it. However, you don't have to be precisely lined up with these objects. It would be quite annoying to have to be lined up pixel perfect with a door to be able to enter it, so the game has a little bit of a leeway. This means that if a door appears on the very left side of the screen, if you enter this door a little bit to the left, your character is treated as being on the previous screen. This is because a character's position, and all sprites in the game really, are referenced from their top left corner. Entering this door in this level, just a tad left of center means that you are technically on the previous screen, which does not have a level transition assigned to it. So in the original game, there is actually a second level transition special object on the screen that leads to the same place as the door. This way, the door will always take you to the right place, regardless of how you enter it. We're almost done, just have to take care of the sprites next. Luckily, this room only has 3 Shy Guy sprites, so this will be pretty easy. All 3 are on the first screen, so the length byte for this screen will be 3 times 2 plus 1, or 7. Pink Shy Guys are sprite number 3, so we just list those out along with their XY position on the screen. These turn out to be hex 03B8, 03F8, and 03FB. The last 2 screens both are empty, so we just add 2 1s to the end of this list, and the sprites are finished. And that's it. These 2 lists encode all of the necessary information to build both a level's background tiles, as well as the sprites and enemies that live in that level. I'd like to make a big shout out to Xkeeper and her Super Mario Bros. 2 disassembly, which served as a very necessary sanity check, especially given all of the weird SMB2 code things. I do most of my research on my own, but if stuff like disassemblies exist already, I will use them as a cross-reference just to make sure I've got everything right. Besides, it's always a nice feeling to figure out something odd that could easily be an error in judgment, like say the background tiles and sprites having different size screen, and then finding comments in a disassembly also questioning why it was done this way. If you'd like to see that disassembly, I have it linked in the description. It's very well done and has a good amount of comments and labeled RAM addresses that makes it easy to follow along what the code is doing. And of course, thank you for watching, especially if you made it to the end of this very, very long video.